Okay.
All right, so there you go.
We in physics one tends to think that mathematics is sacrosanct in the sense that if something is mathematically equivalent, then it means physical equivalence. Um, Turns out that that's not true in the extreme. Um, in my research, our research, we've only found that it's true only if the mathematics was designed for the physics in the first place. For example, calculus was designed for Newtonian mechanics. Um, it's one example, but the Feynman operator calculus is actually designed for quantum electrodynamics. We'll do it here.
Yeah, you roll it.
Oh, just roll it. So my purpose is one, to show that the Dirac equation is actually non-local in time. And in fact, the square root equation turns out to be non-local in space. And yet they're unitarily equivalent. So that clearly means that they don't actually represent the same physics. As an aside to studying the Dirac equation, we notice that the Pauli equation is invalid for S-state discussions. The main reason is there's a finite probability that a Dirac electron will be at the origin. And so the Pauli approximation fails. In fact, to make the Pauli approximation, any approximation of the Dirac equation correct, one needs a cutoff long before you get to QED. My third purpose is to discuss a Hilbert space that was actually designed for Feynman's mathematical formulation of quantum mechanics. This space turns out to contain the Feynman kernel, but it's not in L2, the one that everybody sort of likes to use, and yet the two Hilbert spaces are unitarily equivalent. And the last issue came up because of some work that Andreas gave last time at the last IARD conference. And here we'll show that there actually exists mathematically equivalent classical equations of motion that actually do not give the same physics. So let's start with the Dirac equation. Now, generally speaking, everyone seems to think that the Dirac equation is something that you manipulate with group theory and so on, and manifolds and so on, but no one seems to recognize that actually you can separate the particle and antiparticle wave functions directly, analytically, without any group theory or anything else. And when you do that, you can actually get a different view of it. I'm assuming everyone knows what the Dirac equation looks like, so I'm going to start with arbitrary vector and scalar potentials and write it in two-component form. In this form, where, of course, psi and phi are particle and antiparticle components, so they're two-dimensional. To separate them, it's a straightforward elementary differential equations using integrating factors. Use the integrating factor for the left-hand side of the second one in phi and solve for delta, assume that they vanish at minus infinity, integrate, and we get this equation for psi independent of phi. And then the second equation, we can do the same thing. We can do the same thing for phi to get another one. Now, to actually make a complete decomposition of L2 of R3 comma C4, in other words, split it into two separate spinor equations, we have to find the probability densities, and this is going to be important a little later. So the density for psi is this one, the density for phi is this, and notice that the density and the wave functions analytically, so there's no physics loss. When you do group theory, unitary transformation transforms a wave function. But when you do analysis, you don't transform anything. So we still have the same psi. So any zero of psi in the Dirac equation is zero in this equation. Any eigenvalue can be computed to be an eigenvalue for this equation. Okay. So the point is the separated equation and the densities are non-local in time. Just briefly, go back and let's go back and be a little bit more careful and look at the eigenvalue problem. This is the coupled equation. We can quickly separate it, solve for phi in the second equation, and plug this into the first equation. Do a little calculation, not too much calculus, and we get two separated equations, okay, for the eigenvalue problem. Okay, I went the wrong way. Okay, I'm still going the wrong way. One more time. Okay. If we go back to our equations, if we drop the second equation, if we drop this equation and replace this denominator by 2mc squared, we get the Pauli equation. Okay. We get the Pauli equation. And the density turns out to be just that. This relationship is standard. This is the one that leads to the magnetic field. And so this is the standard form of Pauli's equation. It looks like the Schrodinger equation with an additional spin magnetic moment term. Okay. Now, what's of interest here, the case of interest is obviously when V is, I'm writing it this way, B minus E squared over R, but this is the same thing, where R0 is the classical electron radius. Okay. And A, of course, is a mu P cross R, is the standard spin where it's a line across the phi axis. So these two terms are zero. It automatically means that pi squared is P squared plus A squared. You'll see why I'm talking about that. Notice that this is 1 over R. So we know it's singular at the origin. This is singular also, much stronger singularity, 1 over R squared. And you'll see why I bring this up. Keep doing that, okay? The S state, now in the P state, no problem. The P state electron has no probability of being at the origin. So throwing those terms away, it turns out those terms are like small in P states. But in S states, with a probability of a non-zero probability of being at the origin, you can't throw this term away. You can't replace it by 2mc squared because this term if this term is smaller than, if the R in here is smaller than R0, it starts to explode. Okay. In fact, this term shows up also, and it was thrown away by beta to get the magnetic moment part. Okay, put back into the equations. Actually, put A back into the equation for the interaction representation in QED to account for the Lamb shift and the anomalous magnetic moment using perturbation theory. This density is incorrect because we have an extra term that they also throw away. And that extra term carries the A in there. And A goes like 1 over R squared, and you can't throw it away because it blows up at the origin. Okay. On the other hand, the electron binding energy is 3 eV, and the rest mass is 10 to the, such a quarter of a MeV. The ratio is about 2 times 10 to the minus 5. So if we can replace this by 2mc squared plus E squared over R, and that's valid. Okay, no problem. However, we still need a cutoff at about the classical electron radius. Okay, and this is before we even go to QED. So a lot of the mathematical hullabaloo about covariant quantum electrodynamics is a misdirection simply because not careful analysis of the Dirac equation. In fact, no one can prove that correctly done that the classical Dirac equation cannot account for the enormous magnetic moment and the Lamb shift. Okay. And no one's ever done it, as a matter of fact. But I'm not interested in that. I just want to make one point that the S-state analysis of hydrogen requires a cutoff prior to QED. Okay, now let's go to the square root equation. Woody and I, back in 2005, actually 2000, we started working on the Dirac equation and the square root equation, trying to do it analytically as opposed to using group theoretic methods. And we're interested in the square root equation because it's so important in trying to understand the strong and weak interaction. We constructed a usual fractional powers. The important thing is that it turns out that the people working in harmonic analysis got interested in part of this, and they actually constructed the right representation for the square root equation. Now, what's interesting about this is that this is clearly non-local in space from here, okay? And I want to make a point. Can I use this? Notice that this integration is with respect to y. This function just depends on x. This difference, actually, this blows up at x equals y. You'll see in a second that it does. But the point is that because of this difference, they cancel each other. In other words, the singularities cancel each other, and you get a finite result. Okay. But to really see what's going on from a physical point of view, we need to look at what K2 looks like in terms of K. These are modified Bessel functions of the third kind, and if you're in the United States, and they're McDonald functions if you're in Europe. Okay. Now, K2 is actually K0 plus K and half, and I'm putting K1 half in there because it's actually in between these two. And K1 and K1 half is actually the Yukawa potential. Okay, and the Yukawa potential, everyone knows, was the one that was predicted to account for the strong interaction in nuclear physics. Anyway, here's what it looks like. Now, if you integrate this x minus y squared, it's actually finite. In spherical polars, you get rho squared sine theta cosine phi, I believe, something like that. But anyway, rho squared cancels that out, so it doesn't affect anything. So we're actually interested in the singularity properties of the Bessel functions. So K1 over Z goes, it looks like this near the origin. K1 half looks like, goes like 1 over Z, and K0 goes like ln 1 over Z. Okay. So this term diverges at the origin like 1 over Z squared. K0 is actually integrable. You can integrate the log of 1 over Z, you get a finite number. And of course, once again, K1 half is what's used for the Yukawa potential. Okay. On the other hand, when we go long distance, I'm sorry, keep doing that. When you go long distance, and that is Z much greater than 1, the interaction reverses. K1 over Z goes like, it has a cutoff also, Z to the minus 3 halves, so it goes down very fast. On the other hand, K0 goes down the slowest, has the longest tail. Everything has a cutoff, and it turns out it looks like an identity outside a few Compton wavelengths. Okay. And so thus the square root operator is non-local in space and looks like the identity outside a few Compton wavelengths. This is the important thing. We've already said that the Dirac operator is non-local in time. So physical interpretation of the two as being the same is incorrect. And in fact, the physically correct way to interpret the Zitterbewegung is that at each point in time, the Dirac particle jumps between plus c and minus c to make it look like a point in space. Okay. Now I'm sort of going in a different direction because I'm talking about a couple of different things. Now we know the Follow-Walthusen transformation is a unitary transformation that maps the Dirac operator into the square root operator. The Dirac operator is coupled, the square root is not coupled, so it's another way of diagonalizing the Dirac equation. Okay, it's unitary. Now, what this means from the physics point of view is unitary operators do not preserve physics. It's too crude a tool to say that the physics is the same if you just have a unitary equivalence. That's the point of this. Okay. In fact, Schrodinger and Heisenberg, actually the Heisenberg-Schrodinger relationship was shown to be unitary equivalence between capital L2 and little l2, but it was proven physically long before it was proven mathematically by von Neumann and a few other mathematicians that it was unitary equivalent. And they used the unitary equivalence between little l2 and capital L2. Okay, and in fact, more important for physicists to know is that there are an infinite number of separable Hilbert spaces that are all unitarily equivalent that have nothing to do with physics. Okay, and in fact, a major research area in applied analysis and applied mathematics and mathematical physics is actually to design a particular separable Hilbert space so that you can make it easy to solve a particular mathematical problem that may be of interest to engineers or people in condensed matter physics and so on and so forth. Now I'm going to get a little mathematical, but I don't want you to worry about the mathematics. I want to deal with your intuition, not with your mathematics. Okay? Now, the HK integral, let me tell you a little about it. Kurzweil was a mathematician, applied mathematician working on differential equations with very, very badly behaved forcing functions. So he came up with an integral that allowed him to integrate non-absolutely integrable functions. Now, to be non-absolutely integral is like non-absolutely integral series, non-absolutely summable series, alternating series. That's like the Feynman kernel. E to the ix squared, absolute value is 1, but the integral is finite. It's pi squared over 6, something like that. But it turns out that Hinstock, who actually was a mathematician, was working on it as an extension of the Lebesgue integral. Okay. More important, it's very simple. What it is like if you construct it simply by taking rectangles, okay, but delta is not constant. It depends on an arbitrary positive function. That's the only thing that changes. That means that at each point, the size of the rectangle at the base depends on the function at a certain point in the middle. And so the definition is called HK partition. So all you need to think of is the Riemann integral that we did in calculus and make that small change, and you're in the HK integral. And I'll mention it has a lot of advantages for young people studying theoretical physics. It means that you don't have to learn distribution theory, and you don't have to spend a lot of time learning Lebesgue measure theory. You can go directly to the mathematics you need for quantum mechanics. Anyway, it's an easy definition of the integral. Take the simple case where you're on AB. It's a very simple, almost the same definition that we use for calculus. Okay. And that's all we need to say about that. But let me just make sure you know it's much more general than Lebesgue. Well, you said why? Well, because it integrates e to the x squared, e to the ix squared. Lebesgue doesn't do that. Absolute value e to the ix squared is 1, the integral over r is infinite. But the non-absolute integral is pi squared over 6, for example. And it includes, this next, let me just do the next theorem. Here's clear. If f is Lebesgue integral, then it's HK integral and they're equal. If f is HK integral, and then the sup of the outside sup is finite. That's not true for the Lebesgue integral. Okay? If it's bounded, it's Lebesgue integral. If the HK integral is bounded, it's Lebesgue integral. And this is a simple example that everyone uses. Actually, we could have used e to the ix squared, but I'll come to that later. I'll actually show you how we get the Feynman path directly out of this without a lot of hullabaloo. This function is obviously differentiable, and that gives you this. So another way of thinking of this is that the antiderivative gives you the antiderivative gives you the function back. That's essentially what the HK integral does. Some people call it the Newton integral. Now I want to construct a particular space that we designed directly for the Feynman formulation of quantum mechanics, in particular for path integrals. Now, I'm trying to give you ideas. I don't want you to worry about the mathematics. I don't want your eyes to roll over in your head, So don't worry about the mathematics. The idea. What we do is we say, okay, we have Rn, take every vector that has rational coordinates. Physically, that's all we can compute, so that's all we need. Okay? So I'll have rational coordinates, and around each one put a cube of radius 2 to the minus m, and let m go to infinity. So you have, around each point of rational coordinates, you have a cube, and then you put another cube in there as m gets smaller, 1 over minus 2 to the minus m, 2 to the minus m plus 1, etc. So this guarantees, what it guarantees is this, that if, and define this function, this is the characteristic function, or e is 1 if x is in this little box. It's 0 if it's not. So it's just, we call it a characteristic function. And we just ordered these boxes so that, see, n cross n, in terms of mathematics, the integers are isomorphic to the rational numbers. That's all we're using. We're saying, okay, we can make, I'm trying to get rid of the technicality. The point is that this functional is in every one of the LP spaces. Those are the big spaces. And if any function is 0 for every one of these, then the function itself has to be 0. That's why we have to have all the cubes going down to 0 around every point. That's just a mathematical issue. Here's our definition of the measure, where TK, actually lambda is going to be, and for physical applications, lambda is going to be the Planck time. Effectively, we're assuming that the expected value is going to be, no one can measure lower than the time and the limit of the Planck time. So let me show you what the inner product looks like. Keep going. Okay, now we define our inner product this way. The physical reason for that is not important for what I'm going to talk about. So it looks like this, and in fact, when f equals g, this becomes absolute value squared. Okay. Oh, the sum of those t's is 1. The sum of these by themselves is 1. Okay. So this is the expected value, and this means that this is less than the hence HK integral. So the HK integral is in this space. Okay. I'm just going to quickly show you that this space. I want to go to the. Keep going the wrong way. Quickly, a Banach space is continuous dense embedding if it's dense in the space and its norm is slightly bigger. Okay, then we have the following. Every one of the Lebesgue spaces is contained in this space. This is a Hilbert space. It's separable. Okay. This space is its own dual. It contains the space of measures. In particular, contains the Dirac measure. Okay, that Dirac measure is not in L2. That means we can solve the Schrodinger equation with delta initial conditions. And that means that we construct the path integral directly. The only thing we need now is an extension of the Fourier transform, extension of convolution. And the next result shows you we can do that. Okay? But we can this is just definitions. The important thing is here that the test functions are contained in here. Since it's its own dual, that means it contains the distributions. And I go back to what I said, that when it's designed for physics, it turns out to be much easier. That means that physicists don't have to learn distribution theory, topological vector spaces, Fauché spaces, and so on, so that they can use the delta function and distribution functions for problems. This theorem shows that we could extend the Fourier transform and the relative convolution function. Convolution is as bounded linear operators on the space. Okay. Now we get back to the physics. Since K, it contains the space of measures of all finitely and countably additive measures. In particular, contains the Feynman kernel, and this is a finitely additive measure on sets of bounded variation. Okay. And since the convolution works, this norm is finite in KS2, but in the space of measures, the norm is infinite. And in particular, because the convolution extends as an HK integral, we get the convolution. Okay. And here's how we define what we mean by the path integral. We take the HK partition where the mesh is going to 0, and we set this equal to that. And these are all convolutions. And we define this to be the path integral whenever the limit exists. Well, this is exactly what Feynman wanted, but it wasn't. He couldn't do it rigorously. And notice that it didn't take me a lot of time to get you here. Okay? I could go in detail mathematically without a lot of work. Well, now the following, since KS2 contains 1, the function 1 is in there, then in fact the limit exists for psi equal 1, and we get the standard. That's precisely Feynman's path integral. Okay? We can do a lot more than that. I just wanted to come that far. Furthermore, every orthonormal basis for L2 is orthonormal basis for here. That means that they're unitary equivalent. That's the mathematical statement that they're unitary equivalent. Okay? But they're not the same. Okay? This space contains both the test functions and the distribution, and this one doesn't. Feynman's path integral can be computed here, but not in there. The Schrodinger and the Heisenberg theories can be extended to this space so that we have a space where every physical theory in quantum mechanics has a representation. Right? So they're mathematically equivalent. And as I said before, this one wasn't designed for physics. It was designed long before physics. As a matter of fact, it was designed for geometry. Area, as a matter of fact. Okay. Now, I want to go back to the proper time. I talked about this the last time, but I want to go back and make a very important, let me put it this way. I want to make a very interesting observation. Let's take a particle with the variables x, t, and p, Hamiltonian gamma equals gamma mc squared, where gamma is, of course, the square root of 1 minus v squared over c squared. We can define the proper time in two ways, this way and that way. Square the last equation, and we can rearrange it to get this relationship. If we let this equal b, then we get two different relationships. MC squared over h equals c over b, and CDT is BD tau, and this relationship. Now, clearly, this is obviously identity, but what I want to emphasize here is the mathematics is not the same on both sides. If you use both sides, that's pretty obvious, right? In fact, if we apply it to x, beta is v over c, which is what everybody uses in astronomy and every place else in particle physics, but it's identical to u over b. Now, what that means physically, for no indirect measurements can you guarantee what you're getting. You got to verify that you're actually using v over c and not u over b. And so automatically in astronomical measurements, it's not clear which one's applicable. Some kind of experiment needs to be done so one can decide which one's applicable. Okay. If W is a dynamical function in Poisson bracket, H generates tau T translations. And so we're interested in what happens for tau translations. And for tau translations, we just use the product rule. I mean, essentially the product rule. And this is H over MC squared, and that's B over C. And so we try to construct the Hamiltonian. We did this last time, so I'm not make a big deal about it. We constructed the Hamiltonian. It turns out to be H squared over 2MC squared plus MC squared over 2. And what we see from 16, that no matter what the choice of H is, we always have that this is equal to this. That is, this is the derivative with respect to time in x, and this is the derivative with respect to p. That means that the equations of motion will always be mathematically equivalent. So let's see what that looks like in a concrete case. And I actually take the simplest case. Let me see if I do it right. Nope. Keep doing it wrong. Okay. We take the simplest case and make V a part of the mass. Okay, that means the square of the Hamiltonian disappears. We can construct this real straightforward construction, and what we get is the force with respect to T is gradient of V times this term. This term is positive, okay? Always positive. And when V goes, when R becomes 0, okay, this disappears and we get gradient V. Okay? This term, however, has an interesting property. This is negative, And in fact, when r equals r0, this is minus 1. Okay? And any term beyond that, what was attractive, it's attractive as long as r is greater than r0. It's 0 at r0, okay? But it becomes repulsive if r is less than 0, okay? So physically, this is very interesting. And so physically, it is not the same as that one, although they're still mathematically equivalent, okay? These are my references, and thanks. I'll be glad to answer any questions.